So, ladies and gentlemen, Mr. Chairman, I'm Szabolcs Szávai from Hungary, from the Voice-out and non-profit Ltd, and I would like to give an overview about European project, what we carried out with my young colleague together with the VTT, from the VTT. And this next three presentations will be all the same problem, I guess. So it's a very nice overview of this work, what we do together. So first I would like to introduce what we've done in case of material characterization and numerical simulation of dissimilar metal weld. So, well, we've been mainly dealing with nuclear plants, nuclear components, pressure vessels, connectors, and so on. And we usually have austenitic pipe and ferritic vessels, and this is connected. And this is the key point what we are dealing with the European project, because it's a sensitive point. Well, we usually follow a rather conservative way, because the nuclear area is rather conservative than car industry or something like that. So we would like to find a proper way to how can we handle these dissimilar metal weld problems, because we have in our problem that to determine what you asked, that what is the sensitive point in case of dissimilar metal weld interface, ferritic side, austenitic side, and this should be somehow characterized, and we always have to know where we have to look for the defect. And they also have to know, since we have a dissimilar metal, it's not new information that always have a residual stress, so this also have to calculate and to know the grain size and so on. What is the problem? That in nuclear area is very standard-based area, so that's a very problem that there are no acceptable standard or reliable standard to handle multi-metal components, and we have to investigate and to find the proper way for it. Especially if you would like to take into consideration the stress issue as well. That's why in the last 15 years, several projects deal with this amount weld issue. So I guess many of us who was involved in this kind of project, from ADMU to multi-metal, and is still dealing with this problem. And actually what we've done recently during this multi-metal project, that we made a small-scale mock-up, and we done the material characterization very detailed through the heat-affected zone, and calculated the residual stresses. We carried out the weld simulation calculating the residual stresses, and it was validated by neutron diffraction measurement as well. So what we are talking about, this is in this project, the issue was the safety and nozzle of the reactor pressure vessel. When one side is a ferritic steel, otherwise there is a connecting pipe, and somewhere behind there is a dissimilar metal weld. The mock-up was a very simplified one, but we followed the original welding technology. So our original welding material was bought from Ukraine and Russia, and it was carried out in the original technology, as you can see here. Actually the size is not the same, but the welding technology was the same. So we followed the heat treatment as it was done 13 years ago, and was 30 years ago, and after that the root weld was carried out with the same technology. Actually that's not new technology, but we wanted to have an original equivalent mock-up. Intensity characterization was done during the multi-metal project, and in cooperation with several institutes, concerning VTT, STU, Areva, and others. And not only material, but fracture mechanical characterization was done. This is how the weld looks like, and if we talk about our VBR mock-ups, that always have a ferritic steel, and then three buttering layer. After that, the austenitic weldment and the austenitic connecting pipe. At first, micro hardness map was done, as you can see here on the pictures, And after that, the tensile properties was measured in very detailed way. So several flat specimen was cut from the heat affected zone, and each buttering layer through to the weldment and to the austenitic steel. Here we can see the results of it. So all material curve was measured, sorry, stress strain curve was measured on room temperature and on elevated temperature on 300 Celsius as well. Somehow you can see, for instance, the strength properties, how changes if you go in this direction to the weld. This shows the point from here. And this is the other side. Actually, this point is not that important, but it was we had a chance to calculate it as well. Also, it was measured, as I mentioned, on 300 Celsius, and it was this temperature was decided because this is at the max around the operating temperature of this nozzle, a little bit above it. So we usually characterize the materials on room temperature and 300 Celsius. Here you can see on the elevated temperature of the strength properties of the material, yield strengths and the tensile strengths as well. And the other side of the weld as well. After that fracture test was carried out, 3-point bending, based on 3-point bending as well. You can see the specimen locations in these pictures, and you can see the correct positions. Well, since maybe you can see very well that the interface is not a straight line due to the technology. So it's more or less impossible to put the crack into the interface because you won't catch it. But we wanted to put it in the buttering layers. In each buttering layer, we wanted to have at least one crack in buttering 1, 2, and 3, and the base metal close to the heat affected zone and in the weld as well. Okay, it's not very important, but you can see some pictures how it was done. But the results. Actually, you can see the cracks. Unfortunately, in this case, there were no side notches, so maybe the crack was not very straight, but it was possible to evaluate somehow. And you can see how the G1C changes in this way. And very well visible that the critical point is somewhere in the buttering. Well, also, since if you cut something, it will lose the residual stress. That's why also instrumented hardness test was carried out and compared with the tensile properties. And there are some good agreement, and there is a certain shift. What we believe that is just because of remaining residual stress. Here you can see the macrography, and very well seen that how the ferritic steel heat affected zone appears, and the austenitic grains can be recognized. After that, if we have a proper material properties, we were able to carry out the detailed simulation of the welding to know the residual stresses, and later it was used for other purpose for the next presentation. We used the Mark MSC code combined with Simufact welding software, and actually, since we had only measurement for room temperature and 300 Celsius, some kind of database, the GMAP software was used to generate the material properties up to 1500 Celsius, and it was fitted to the room temperature and elevated temperature curves as well. So we think that it was reasonable and good. And after that, the simulation was taken into consideration all the steps of the welding technology, including the heat treatment as well. And all welding path was taken into consideration. We were lucky because in our case the welding path geometry was well known and we could catch it from the micrographic. So here you can see some results of it, mainly the residual stress after the buttering, first and up to the 3 layers, and you can see the longitudinal and plate normal direction stresses. It can be seen that we have quite high stresses. After that, the butt weld was modeled as well, and you can see on this picture how the residual stress changes in the sigma 1, sigma 2, and sigma 3 directions, and also the martensite and bainite fraction was calculated as well. This calculation was validated. In this picture, we show that the distortion, we put it together, maybe that you can see the finite element mesh and the weld behind. And if we see the distortion of the plate after the welding and compare with the finite element modeling, we have very good agreement. It was also measured in the GRC by Newton diffraction test, the residual stress, and we found that quite good agreement between the calculation. Of course, there are some scattering in the measurement, but this dashed line shows that the calculated results, and it's quite good. So it's very unusual if we have very good fit to the residual stress measurement. So we think that in this way we were able to characterize the dissimilar metal weld properties, and we were able to determine the residual stresses. That is very important, and also all kind of very important fraction mechanical properties was measured. So we have now very detailed information about our weld safety and nozzle. So thank you for your attention.